Hello and welcome back to Elementary Algebra. I am your instructor, Amy Fuchsteiner, and today we are going to be working on elimination as a method of solving systems of equations. Sorry, I've got a light source that's being a little bit picky this morning. So we have done systems of equations by graphing, and we have done systems of equations using substitution. What we're going to do today is give you a third tool for your mathematical tool belt, and this one is referred to as the elimination method. It is sometimes known as the addition method. The idea here with this particular method is that if you have two sides of an equation that are equal. Here I have the x plus 5 on one side of the equation and the 7 on the other side of the equation, that if I add or subtract the same thing to both sides of the equation, it doesn't matter what it is. If we were going to solve this, we would add 5. But I am just going to add a y value to both sides of this equation. I can add anything to both sides of an equation. And what I get in the end, x plus y plus 5, has to be equal to the other side. I'm using what's known as the addition property of equality to say if I add equal things to both sides of the equation, the equality is maintained. I haven't changed it. Practically imagine this. If you have two children and they each have the same amount of money, let's say one has $100 and the other one has $100. The only way you're going to keep them both happy is if you give them each the same amount of money again. You have to add or subtract the same amount of money from that $100 in order to keep those children happy or equal, right? So the idea with this elimination / addition property is that we are going to be adding, and in some cases subtracting, the same thing to both sides of an equation, or equal amounts to both sides of the equation. Now, this particular method is so slick. It is so nice, particularly when it is set up for you. Let me show you what I mean. Okay, so in problem number 1, we have this x plus y is equal to a negative 4, and we have x minus y is equal to 8. This is the perfect setup to use the elimination method because of this situation right here. These guys are opposites. So if I have a minus y and a plus y, if I add them together, they will cancel out because they are opposites. So what we're going to do, I'm going to use my red one here, is we're going to take these two equations, which, by the way, are also lined up. My x's are lined up, my y's are lined up, my equal sign is lined up, and my minus 4 and 8 are lined up. And I'm just going to add them together, right? So I have this first equation, left side, right side. And if I look at the second equation, the left side and right side are equal. And like we set up here, if I add equal sides, two equal sides, I've maintained the equality, right? Okay, so I have x plus x, which is 2x. I have a minus y plus y, which is a 0. Then I have a minus 4 plus 8, which is 4. Do you see the mathematical thing that happened here? So now the y's have disappeared and I only have x's left. I have 2x is equal to 4, which to solve for the x, I'm going to divide both sides by 2. So now I know x is equal to 2. Now, just like we did before, I'm going to take this x is equal to 2, and I'm going to put it into one or the other equation. It won't matter which one. I'm just going to use the first one. So I'm going to have, let's see, that's going to be a 2 plus y is equal to a negative 4, or 2 plus y is negative 4. Subtract 2 from both sides, still using that addition property, and I get y is equal to a negative 6. So I found both my x value and my y value. I believe that the point 2 comma negative 6 is a solution to this system. If I'm not confident, or if I'm new to this, maybe what I do is I check to make sure. So 2, negative 6. That in the first equation would be a 2 plus a negative 6. That's a negative 4. That one checks. In the second equation, that would be 2 minus a minus 6. That's 8. That one checks. And I am certain that 2, negative 6 is the solution to this system of equations. All right? Beautiful. Problem number 2 is also perfectly set up for elimination. I say this because, again, as I'm looking at this problem, I have 3a plus 2b is equal to 8. And notice that for the second equation, I have a minus 3a. They're not only opposites, but they are lined up. I have a plus 4b. B's are lined up right underneath each other, equal to, lined up, negative 26. These guys are opposites. So I'm just going to go ahead and add these two equations together. I've made sure that they are all lined up and sweet. So the 3a minus 3a will cancel, and I will have 6b is equal to a negative 18. Dividing both sides by 6, I get b is equal to a negative 3. And I found one of my variables. Now I'm going for the other one. To find the other variable, I want to put that value of b into either equation. It won't matter which one. I'm going to do the first one again. Whoops, I want my red. So I have 3a plus 2 times, I'm going to put that b in, negative 3 is equal to 8. 3a minus 6 is equal to 8. Now I'm going to add 6 to both sides. That gives me 3a is equal to 14. Dividing by 3, I get a is 14 over 3. It's not a good fraction, but it's still an answer. I believe I have an answer of 14 over 3, comma, negative 3. To check this one, I'm again going to pull out my tool here. This is the calculator with the fraction buttons on it. All right, so in the first equation, I would have 3 times 14 over 3 plus 2 times a negative 3. All right, so 3 times, I'm going to do 14 over 3. That's 14 minus 6, that's 8. Yep, it worked in the first equation. But as a reminder, if it really is a solution, it's got to work in both. So now I've got to do a negative 3 times 14 over 3 plus 4 times that negative 3. Yeah, okay. So I'm going to do negative 3, and then in parentheses, 14 fraction 3. And I get a negative 14. 4 times negative 3 is minus 12. That is a negative 26, and it works. So I am certain that that is a solution to the second equation. Still good. Third system of equations. I have x plus 2y is equal to 8, and 3x plus 2y is equal to 20. Did I say plus? This is x minus 2y is equal to 8. Notice that the 3x lines up with the x. The y's line up. The equal sign is in a line, and then I have the 20. I also have opposites here with a positive 2y and a minus 2y. That makes this a perfect candidate for elimination. So I'm going to add the two equations together, and that's going to give me 4x is equal to 28. Dividing both sides by 4, x would be equal to 7. Once I have an x value, I can then put this into either equation, the first equation or the second. I'm going to go with the first equation. The first equation, x is 7, so that'll be the 7 minus 2y is equal to 8. So I'm going to put that 7 in there. So I'll have 7 minus 2y is equal to 8. Subtracting 7 from both sides, minus 2y would be 1. Dividing both sides by a negative 2, I get y is equal to a negative 1/2. Again, for those of you, that's a minus 7 from both sides. And I'm going to divide both sides by negative 2. All right, so I think I have a point, a solution to this system at 7 comma minus 1/2. Now, again, to check this, I can put the values into each equation. This would be 7 minus 2 times 1/2. If you're unsure, go ahead and use your calculator. 2 times, is that a negative 1/2? Yeah, it was. Okay, I knew I was forgetting something. So 2 times negative 1/2 is indeed a negative 1. So this would be 7 minus a negative 1, which is 8. And that checks with this equation. The second one would be 3 times 7 plus 2 times a negative 1/2. I know 2 times a negative 1/2 is a minus 1. 3 times 7 is 21. That's 20. And oh, look, it checks. There we go. So I know for sure that 7 negative 1/2 is a solution. All right. So that is an introduction to the elimination method. Now, you know we're not going to keep it this simple. You know we're going to kick it up a notch. That's what we do. It's part of what happens. So let's take a look at how we can make this, what kind of difficulties, maybe I'm not trying to make it difficult, but what kind of difficulties you might find. For example, so far at every one of these, it was set up so that we had opposites, a 3 and a negative 3, 2 and a negative 2, a y and a negative y. So we were set up for perfection here for the elimination method. Let's see what happens in some of these examples where this elimination method is not the perfect setup, right? Okay, so here is one where we are going to add a step where we may need to multiply one or both of the equations in order to help them be a perfect setup. Here I have 3v minus 4w is equal to a negative 7, and 2v plus w is equal to a 10. All right, so the idea here is that the v's are not the same. I would want them to be opposite. I would want a 3 and a negative 3 or a 2 and a negative 2, and that would be the perfect setup. This is not close. I would not choose v's. If we look at the w's, I would want them to be the same letter, but opposite signs, one positive, one negative. Ooh, I have that. But they would both need to be the same number, a 4w, and that's a 1w. I would want this to be a 4w. So if given a choice of changing v's around, where I would need to change both numbers, or changing w's, I can see that if this was a 4, I would have a perfect setup. So I'm going to multiply that second equation by 4. The entire equation or each side, however you need to think of it. That means that I would have 3v minus 4w is equal to a negative 7. I'm going to keep that first one exactly the same. I'm not changing anything. But I'm going to use that multiplication property of equality to say if two sides are equal and you multiply them by the same thing, the result will still be equal. 8v plus 4w equals 40. And now I have set up my w's as opposite. Now I have 3v plus 8v equal to a minus 7 plus 40. That's 33. The w's are eliminated, hence the name elimination method. Because when you add equal quantities to equal quantities, you maintain the equality. Now I'm going to divide both sides by 11. And I have a value of v of 3. Now I'm going to put that in. I'm going to do the first equation. So I'm going to have 3 times whatever v is, which I just found, minus 4w is equal to a negative 7. That's a 3. So that's going to be 9 minus 4w is a negative 7. I'm going to subtract 9 from both sides. Minus 4w is a negative 16. I'm going to divide both sides by negative 4. So I have w is equal to a 4. This means I believe I have a solution of 3, 4. And to check it, I'm going to put 3 in for v. So 3 times 3 minus, and w in for 4. 4 times 4. That's 9 minus 16, which is negative 7. That one checks. And in the second equation, I'm going to have 2 times 3 plus 4. That's 6 plus 4. That's 10. And that one also checks. There we go. I got it. I know 3, 4 is a solution to this system of equations. Beautiful. All right. Let's look at problem number 5. Problem number 5 is along the same lines. We have a 2x minus 5y equal to a negative 9. And we have an x plus 7y is 7. Or 5. Sorry, x plus 7y is equal to 5. Oh, sometimes the biggest mistake is just copying these suckers down wrong. It is. All right. If we look at the x's, here I have a 2x. And if I want to eliminate the x's, I need to have a negative 2 here. I don't. But let's see what the y's are. If the y is a negative 5 and that one is a 7, there's nothing I can multiply a 5 by to get a 7, and there's nothing I can multiply a 7 by to get a 5. So I'd actually need to multiply both of these to find a common number. So right away, I'm thinking I don't want to do the y's. I'm thinking I want to do the x's to use the elimination method. And I'm going to need to multiply both sides of this equation by a 2. And if I want it to cancel, I need it to be a negative 2, right? Because positive, then this one should be negative. So that's going to give me 2x minus 5y equals a negative 9. I'm rewriting the first line again. Then I'm going to have a minus 2x minus 14y equals negative 2 times 5, a negative 10. I've chosen to eliminate the x's, and I've set it up so that they will eliminate. So I'm going to circle those, because those are the ones I wanted to eliminate. Then I'm going to add. That's just going to be a 0. They will be eliminated or cancel out. Minus 5y minus 14y is a minus 19y equals minus 9 minus 10 is a minus 19. Dividing both sides by a negative 19, I get that y is equal to 1. Now, I need to take this value of y and put it into either of the two equations. I'm going to put it into the second one, just to show you that it should not matter. That's going to give me an x plus 7 times that substitution equal to 5. So I have x plus 7 is equal to 5. Subtracting that 7 from both sides, I get x is equal to a negative 2. This gives me a solution for the second unknown variable. And I think that the solution to the system is a negative 2, 1. To be sure, I'm going to put in a negative 2 for the x. So 2 times a negative 2 minus, and I'm going to put a 1 in for the y. 5 times 1. That's negative 4 minus 5. That's a negative 9. And it checks. And remember, I can't just do it for one equation. I need to check both. So if I check the second equation, that's going to be a negative 2 plus 7 times 1, or negative 2 plus 7, which is 5, and that indeed checks. And so I know negative 2, 1 is a solution to the system of equations shown in problem number 5. Problem number 6 kicks it up, right? So just when you've gotten used to this and you know, okay, I need to multiply 1, I'm going to show you what to do with a question like number 6. All right. So if we look at number 6 gives us 4a plus 7b is equal to a negative 8. That's our first equation. Second equation is 5a plus 6b is equal to a 1. Now, if I look at the a's, there is not a number I can multiply 4 by to give me 5, and there's not a number I can multiply 5 by to give me 4. So I would need to find a common multiple of both 4 and 5. Okay, let's look at the b's. Got a 7 and a 6. There's nothing I can multiply 7 by to get 6 or 6 by to get 7, so I would need a common multiple of 7 and 6. So this is how I analyze the problem, and this is how I make a decision. Do I know a common multiple of 4 and 5 right off the top of my head? Why, yes, I do. I know a number that both 4 and 5 go into, and that's 20. So because my brain jumped to 20 first, I'm going to go with 20. Could I have done 7 and 6? Yeah. Common multiple for 7 and 6 is 42. I could have gone with 42. But since 4 and 5 are more familiar to me, I'm going to go ahead and use the 4 and the 5. So the common multiple for 4 and 5 is a 20. So I'm going to try to raise both of these coefficients to 20. I need one to be positive and one to be negative. So I'm setting up a situation like right here where they can cancel out. So what I'm going to do is I'm going to multiply the top equation by 5 on both sides. That's going to give me a 20a plus 35b is equal to a negative 40. And in order to get a 20 on the second equation, I need to multiply by 4. But if I wanted to cancel, 4 times 5 is a positive 20. I need to multiply by a negative 4. Okay, that's going to give me a negative 20a, negative 4 times 5. Negative 4 times 6 is a minus 24b, equal to a minus 4. Look how these two are now opposites, right? Those two are opposites. Okay, adding the two equations together to eliminate one of the variables will give us 11b is equal to a negative 44. Oh my gosh, there was a lot of sort of heavy lifting going into that, but look at what I get. Look at how beautiful that is. 11b is equal to a negative 44. Now I'm just going to divide both sides by 11 to get b is negative 4. So straightforward if you can get through that mess on the top. Okay, now I'm going to take that b is equal to a negative 4, and I'm going to put it into either one of the original equations. If you spent a lot of time messing around, you could have some mistakes in all of this work. So the idea is to go ahead and put this into one of the original equations from the system. So I'm going to do the second one. Doesn't matter which one. 5a plus 6 times your b value has to equal 1. My b value is a negative 4. So that's going to be 5a minus 24 is equal to 1. Add 24 to both sides. 5a is 25. Divide. What's a divide? Divide both sides by 5 to get a is equal to 5. Now, I believe the solution to this system is the point 5, negative 4. To be certain of this, I'm going to put the 5 and negative 4 into the first equation. 4 times 5 plus 7 times a negative 4. That's 20 plus a negative 28. That's a negative 8. And then I'm going to check it against the other side. It worked. Then I have 5 times 4 plus 6 times a negative 4. Is that 1? That's 20 minus 24. Is that, it's 5 times 5. Oh, I knew I was making a mistake. 25 minus 24. Yes, that is 1. Okay, it works. I thought all of that, and I'm going to have a mistake. Nope, I did all right. Okay. Good. Beautiful. Oh, my Lord, Amy. Okay. So these are some really intimidating questions. Okay. Before I tackle this, pause me, go get like a drink, take a stretch, whatever. Give it a minute. I'm going to take a sip of my coffee. Okay. Ready? Here we go. These are some ugly looking systems. Yeah. So what would I do? Okay, let's take a look at problem number 7. Problem number 7 is a system that is 1/6 x plus 1/2 y is equal to 1/3. And then I have 1/9 x minus y is equal to a negative 5/9. Okay, couple of things. First of all, there is what is probably a more efficient method. And I can see a very efficient way of doing this real quick right now. But if you're not comfortable with fractions, there is no shame in looking at the fractions first and eliminating them. What do I mean by that? We've talked about this before. We did this in one of our earlier chapters. Do you see how this one has a 6, a 2, and a 3? What's a common denominator for 6, 2, and 3s? I'm going to multiply this entire equation by 6 on the left side and the right side. The 6 and 6 here are going to cancel, giving me just a 1x. The 6 and 1/2 here, I got to distribute it, is going to give me 3y. The 1/3 of 6 is 2. And I've eliminated the fractions in that particular problem. Now, the second one, I have 9ths, right? So I'm going to multiply the second equation by 9. And when I do that and distribute through, that's going to give me 1x minus 9y is equal to a negative 5. Okay, now my system has changed slightly. But do you notice the first numbers? The first numbers are now a 1x and a 1x. So I could just take this second equation and multiply by a negative 1. Because remember, to use the elimination method, we need a positive and a negative. So I'm just going to multiply this through by a negative 1. So now I've got x plus 3y is equal to 2. That equation has not changed from the beginning. Minus 1x plus 9y is equal to 5. Beautiful. Gorgeous. Same variable, same coefficient, opposite signs. So when I add these two equations together, because equality gives me equality. Dividing both sides by 12, I get y is 7/12. Oh, of course, it's going to be an ugly answer. That's okay. That's okay. These things happen. Now I need to take this and put it into either one of the equations. It's kind of a crapshoot. I'm going to need to use my fraction button on my calculator no matter which one I do. So I'm just going to choose the hard one. I've got 1/6x plus 1/2 times the y equal to 1/3. All right, so this is going to be 1/6x plus 7/24 is equal to 1/3. All right. If you don't know how to do it, it's time to get comfortable with the fraction button. I'm going to subtract 7/24 from both sides. Well, yeah. 1/3 minus 7/24. So I have 1/6x is 1/24. Now I'm going to divide 1/24 by 1/6. And I get x is 1/4. Oh, I got it. Okay. So I believe I have an answer here of 1/4, because remember the x comes first, 7/12. Now I want to check it in both equations. Okay. So in the first equation, I'm going to have 1/6. Sorry, I'm running out of room. I have 1/6 times 1/4 plus 1/2 times 7/12. So that's going to be 1/24 plus 7/24, which is 8/24. Yes, that's 1/3. Okay, so thank goodness that one checked. I hate when I have to do fraction ones over and over again. Then I've got 1/9 times 1/4 minus 7/12. So that's going to be 1/36 minus 7/12. Okay, fractions. 7/12. I got to get it to 36. 1/36 minus 21/36. I'm going to multiply both by 3. That's a negative 20/36. 20 and 36 are both divisible by 4. So that's going to be a negative 5/9. Yeah, yes. Done. Okay. All right. Problem number 8. Amy, why do I have to give you such hard ones? Oh, I got a big bold, this guy. Put a box around this guy. Big bold. I worked hard for that solution. I need to mark it. Okay, problem number 8. Problem number 8 is fine, but we can simplify this. 2 times 4x plus 11 is equal to a negative 12y. 3x, is 2y plus 8. Okay, so in the first equation, I'm going to go ahead and distribute. That's going to be an 8x plus 22 is equal to a negative 12y. And in the second equation, I don't have my x's and y's on the same side. So I'm going to move that 2y back. And then if I look at that first equation, I've got to swap these two. So that means I'm going to subtract. Oh, I need to work on this guy a little bit. So 8x plus 22 is equal to a negative 12y. I need the constant on the other side. And I need the 12y back over by the 8. So that would be 8x plus 12y is equal to a negative 22. Okay, so now things should line up. 8x plus 12y is equal to a negative 22. And I have a 3x minus 2y is equal to an 8. Okay. Now my x's are lined up, my y's are lined up, my equals are lined up. Standard form, ax plus by equals c. Now, the 3 and the x, there's no number I can no whole number. I can multiply 8 by to get 3 or 3 by to get 8. So I probably am not going to mess with the x's. Here I have a positive 12y and a negative 2y. If I multiply the 2 by 6, I will get 12. They're already opposites. So I'm going to mess with those y's. I'm going to multiply this side by negative 6 and this side by negative 6. So that's going to give me 8x plus 12y is a negative 22. And a negative 18x. Oh, I don't want it to be negative. I want it to be positive, don't I? Yeah, because a negative will change the sign. So this should be a positive 6. There we go. That's not going to change the number, but it will change the sign. So that'll be an 18x minus 12y, because I need these two to be opposite signs, and they already were. And if I multiply by a negative, that's going to change the sign. So I don't want to do that. Equals 8 times 6 is 48. Okay. Now, do you see how these are opposite in sign and the same number? Okay. That's going to give me, red pen, 26x is equal to 26. I love when this happens because now I just divide both sides by 26 and I get that x is equal to 1. And once I know that x is equal to 1, I'm going to put it into the second equation just because the second equation looks a little bit easier. 3 times 1 is going to be 2y plus 8. Remember, I want to use the original equation because if I messed up in here, this original equation is where it's at. So I've got 3 times 1. I'm going to subtract 8. So negative 5 is 3y. And I'm going to divide both sides by 3. So I'm going to have a negative 5/3 is my y value. So I think I have an x value of 1 and a y value of negative 5/3. So I believe that my answer is 1, negative 5/3. Now I can check that answer by putting them into the original equation. So I'll have 2 times 4x, 4 times 1, plus 11. Okay, so I need to double up there. Yep. So that's going to be 2 times 4 plus 11. That's going to be 2 times 15, which is 30. Does that equal a negative 12 times a negative 5/3? Oh. 4x plus 11, that's 4, that's 2. I've got 5/3. That's going to be a 60 over 3, which is 20. Ah! Okay, I got a wrong answer. So now I got to look back at all of this and figure out what went wrong. Okay, I'm going to start from the beginning. 2 times 4x plus 1. That's going to be 8x plus 22 is a negative 12y. So I've got 8x plus 12y is a negative 22. I do believe that's right. Okay. Then I've got 3x. I'm going to subtract the 2y is 8. 3x minus 2y is 8. So I've got an 8x plus 12y is a negative 22. I'm going to multiply both sides. It's going to give me an 18x minus 12y is 48. 26x. Did I jump the gun here? No, negative 22 plus 48 is 26. Dividing both sides by 26, I do get x is equal to 1. I'm going to put that one into that equation. Oh, do you see what I did? You probably saw it when I did it because I'm talking. This should have been a 2. I see it. Somehow I changed that into a 3. Nope, that's a 2. And if that's a 2, then that's a 2. And then when I put it in here, negative 12, that's 2, that's 30. Aha, and it checks. Oh, thank Lord, it wasn't a whole lot of stuff. Okay, so now when I check my second one, I've got 3 times 1 is equal to 2 times a negative 5 halves plus 8, or 3 is equal to negative 5 plus 8. That's a 3, and that one checks. Okay, I do have the correct solution. I did have a slight error. I did need to change 5/3 to 5 halves. It was not a mathematical error, but rather I copied the problem down wrong as I went along. This is not an unusual mistake for you, for me, for anyone. Okay. What have I got next? Oh, consistent and inconsistent systems. Okay, we talked about how there are 3 different types of solutions. An inconsistent solution, a consistent solution with a singular solution, and a consistent dependent system which has infinitely many solutions. In other words, one line is simply a copy of the other. So let's look at these. If I'm going to solve this particular system, here I've got 4x minus 8y is 36, and 3x minus 6y is 27. So to solve this system, I think I want to go with x's because 3 and 4 can both be made into a 12. And that's pretty nice. 8 and 6 would get me to 48. I don't want to do that. Okay, so I'm going to take this first equation and I'm going to multiply it by a 3 on both sides. And I'm going to take that second part and I'm going to multiply it by a 4. But I'm going to multiply it by a negative 4 so that it cancels. That's going to give me a 12x minus 24y is equal to 36 times 3 is 108. The second equation will be a negative 12x plus 24y equal to a negative 108. Now, when I add them, these guys will cancel out. So I'm going to get a 0 there. Uh-oh. Minus 24y plus 24y is a 0. Minus 108 plus 108 is a 0. Look at that. All my variables were eliminated. But I do have a true statement. What do I mean by a true statement? I mean I have 0 equals 0, and that is a true statement. All my variables are gone, and I have a true statement. We talked about this. All my variables are gone, and I have a true statement. Because I have a true statement, that means that this is the infinitely many. Right? Basically, this means that one of these equations was essentially a copy of the other, made to look different. So when I change the sign on the second one, effectively subtracting it, of course I'm going to get 0 equals 0. So this will be infinitely many solutions, or if you'd rather, from negative infinity to infinity. That's what it looks like to get an infinitely many solutions when you're doing elimination. Basically, you're subtracting the equation from itself, the first linear equation from the second, and you get a 0 because it's a copy of itself. So when you subtract it from itself, you have nothing left, right? That means that if we were to graph these lines, we would have essentially gotten one line right on top of each other. This third version over here. We would have had infinitely many solutions with one line on top of the other. Okay. What about problem number 10? Let's take a look at problem number 10. Here I've got a 2x and a 3x, a 4x and a 6x. I'm going to go with the 2's and the 3's. I'm going to multiply this guy by a negative or by a 3. Let's do a positive 3 on the first one. I just like that better. And then I'm going to do a negative 2 on the second one. Right? Because 2's and 3's will both go into 6's. I need one to be positive and one to be negative, so that when I add them, something cancels. This will give me a 6x plus 12y is equal to a 45. 15 times 3. Then I'll have a negative 6x minus 12y. 18 times 2 is a negative 16. Look at this. On purpose, my 6's are opposite in sign, and the x's will indeed cancel out when I add the two equations together to eliminate a variable. This will cancel out, but so do those. But now on this side, I have 45 minus 16, which is, I think, 29. Once again, all variables were eliminated. But this one is different because I have a false statement. In this case, I have 0 is equal to 29. That is not true. Not true. 0 does not equal 29. What does that mean? Well, if all your variables are eliminated and you end up with a false statement, this is what it looks like to get a no solution. You have an inconsistent system. You have a system that makes no sense. It is inconsistent. And when you go to graph these two lines, they will look parallel. There is no intersection. When there is no solution, this means that there is no intersection. So in this particular case, this is what it looks like to get a no solution using the elimination method. Basically, you get a false statement, like 0 is equal to 29. And most of the time, this problem is over in a snap, like as soon, just like this first one, right? Problem was over really quick. We just canceled everything out. Here, looks like we canceled everything out, but it's not a true statement. So for consistent, dependent, and inconsistent no solution, problems are over super quick, right? Okay, so if we look at problem number 11, Amy gave you one with all kinds of fractions again. What was Amy thinking? I am going to multiply this one by 6, this one by 6, and that's going to give me 6 over 2 is a 3x, 6 over 3 is a 2x, 1 times 6 is 6. And I'm going to multiply this one also by a 6. That's going to give me 1x, 6, 2 plus, oh, that should have been a y. There we go, plus 10y is equal to a negative 54. Then I'm going to multiply this one by a negative 3, because that will make my x's go away. Oh, I'm going to get some big numbers. 3x plus 2y is equal to 6. Then I'm going to have a minus 3x minus 30y is equal to 54 times 3 is, I think, 162. I don't want to mess that up. 50. Yep. Okay, good. All right. So now you can see I've got these two the same. I'm going to add them together to get a negative 28y is equal to 168. Oh, man. So I'm going to take that 168 and divide it by a negative 28. Oh, look at that. I got a y value. Y is equal to a negative 6. Okay, now I'm going to put that y value in to the original equation. X over 2 plus something over 3 is equal to 1. I'm going to use that negative 6. So I've got x over 2 minus 2 is equal to 1, or x over 2 is equal to 3. So x would be a 6. I believe I have a solution here at 6, -6. Okay, I ran out of room to check it. It's okay. So, again, you have on this particular problem set the 3 different outcomes. The first outcome, you have a true statement, everything canceled, no variables left, and you got a true statement like 0 is equal to 0. This is a consistent dependent solution. It means that one line is a copy of the other, and that if you were to graph them, they would essentially graph the line on top of itself. The second solution is what happens using elimination when you get a no solution. You get a false statement such as 0 is equal to 29. The variables are all eliminated when you go through the elimination process. This is what a no solution looks like. This is an inconsistent system. The answer is no solution. There is no solution. The lines themselves, when drawn, would be parallel. For problem number 11, we have a consistent system because we got a singular solution. This tells me that when I graph the lines, they will intersect. Right. Now, the last goal for this particular section is one that just sort of reminds you of the 3 different methods and asks you an opinion on which one you would use to solve. So to go over, there are 3 different methods for solving a system that is 2 equations, 2 variables of equations. The first is the graphing method. The graphing method is used if you have y equals mx plus b form, or if you can quickly put the numbers into the equation, into y equals mx plus b form. You must have a graph available. Yeah, the graphing method is kind of a stickler because you've got to have the y equals mx plus b form, and you've got to have a graphing paper, graphing utility available. It has some cons, right? Why not? Why wouldn't you use the graphing method? Well, if you don't have y equals mx plus b form, if you don't have a graph available, maybe because you need precision. The problem with the graphing method, the major problem with the graphing method isn't necessarily y equals mx plus b or the graphing availability. It is the fact that you are interpreting where the solution is by looking at the point on a graph. And you remember sometimes when we graph the lines, the intersection was not like at the point 2, 2. It looked like maybe it was at 1/2, 3/4, and it ended up that it was at 5/8 and then 9/16. So there's no way to be precise when you're reading that point of intersection from the graph itself. It's one of the reasons we don't use the graphing method a lot. The substitution method, you want to make sure that you've got a y equals or an x equals that you can solve quickly for one of the variables, and then you simply put it into the second equation or the other equation. We oftentimes do not use a substitution method if there are a lot of fractions. We would not use a substitution method if there are a lot of fractions or if there's a lot of lead work to solve or to isolate a variable. Okay. The elimination method is we get a common coefficient with opposite sign. And then we add the 2 equations together. Why wouldn't we use the elimination method? Because it's hard to find a common coefficient. And sometimes because we're not in the ax plus by equals c format. We're not in standard form. Now, that being said, substitution method, elimination method, there's really not a difference in outcomes in terms of these two. Basically, what we're trying to do is just give you some different tools for your tool belt, for your mathematical tool belt, so that when you come up against problems, you can analyze the situation a little bit and make a decision as to what could be the best. So if you're looking at these 4 problems, I just want you to give some idea of what could be a pro or a con. If you look at problem number 12, I have y is equal to 3x minus 5 and y is equal to a negative 2x plus 1. Both of these are in y equals mx plus b form, right? They're also both solved for y. So if I was looking at this particular system, the first, 2 options that would come to my mind is first, do I have graph paper? Because I could very quickly graph both of these and find a solution, right? The second thing that comes to mind is the substitution method, because it's already solved for y. So because both equations are already solved for y, I could do the substitution. I could take that y out and put in 3x minus 5. And then I have one variable and I could go ahead. So I would say, for me, my top 2 choices here would be graphing or substitution. That doesn't mean I can't do elimination. Elimination is absolutely possible here. It just may take a little bit more work. Like, it might take a little bit more setup, right? All right, let's take a look at number 13. If you look at number 13, we have solved for y. I do have one of these is solved for y. Not both of them, but one of them. So when one of them is solved for y and the other is not, this is a great setup for substitution. Because I can take this bit and put it in for the y real quick and be done. It's already set up. In a similar fashion, looking at number 14, where I've got a 2x and a minus 2x, this guy is already in the form ax plus by equals c. So both equations, in other words, the variables are lined up. We've already got opposite coefficients on that x. So while I could use elimination, or I could use substitution, and I could graph it, this guy is set up perfectly for elimination. It's just automatic setup. I can go from there, just quick step. Now, what about 15? Well, 15 is already set up in ax plus by equals c. So that's a pro for elimination. But I could, if I don't feel comfortable with elimination, particularly because there is some lead time, I would need to multiply the top equation by something and the bottom equation by something. Oh, if I was going to use elimination, I wouldn't mess with the x's. I would only mess with the y's. And that would mean multiplying the top equation by 2. So I would probably do elimination here. But you could just as easily do substitution. I could solve for that y. That would work okay. So elimination would be my first choice, but I could do substitution here. And as long as I want to solve, I could graph. Although I'd have to have graph paper, and there's a lot of lead set up in getting this one to graph. But if that's where I'm most comfortable, that's the skill I would go with. All right. So that's what I've got for elimination. Now that you've seen all three types, the graphing, the substitution, and the elimination, we are good to go. Thank you. And I'll see you again next time. If you have any questions, please don't hesitate to reach out to me or to contact the Math Center. They'll happily go over things with you. All right. Thank you.